Okay, so let's start. To refresh our memory. Are you almost ready for the midterm? Did you at least cover most of the material yet? Okay, nope. Let's start. One second. Fix something in this. So let's start. The worst case for search, insert, and remove operations in a binary search tree is what? Again, try to answer yourself without discussing it with your friends. We said the binary search tree that we learned so far, the operations for searching, inserting, and removing, and why we say searching, because that's the whole idea of the binary search tree, is to search. Let's wait for everyone to answer. Of n, of log n, search, O of log n, insert, and remove of n. Who wants to remind me why the search is O of log n? The search part is O of log n, and not the insert and remove. James.
Because if it's an best case, it's increasing each time it doubles. So that way.
Very good. So the key word that you said is if it's what? And the question is about worst case. So we shouldn't include the log of n because we're asking about the worst case. So that means, guys, no, it's not log of n. It's going to always be O of n because we're saying what is the worst case of a binary search tree. Okay, guys? I want you to now, at this point, the midterm is in 2 days. Maybe it's hard for you to click it, just memorize it at this point. Okay? Which binary tree will end up costing O of n? This one or this one? Which one will cost O of n?
I want to see.
We have this tree, and we have this tree. Same thing, search, remove, insert. And operations. What is the cost of the operations? Guys, just answer it, please, without discussing. We still have around 20 people, so please try everyone to answer it. Exactly, 99%. That's very good. Okay. Yes.
I'm sorry, it's off topic, but for the midterm, should we review what those?
Not the proofs itself, but you need to know these things. Now, if you understand the proofs, that means you don't have to memorize, then you'll be able to do it. But no, you don't have to actually mathematically prove anything. No, I'm not going to ask you to mathematically prove something. This is too complicated. So guys, who can help me to understand why in a binary search tree this one is going to end up with O of n and not this one? Why not both?
Because normally it's always O of H.
Very good, very good. So because I want you to always understand the costs and the efficiency is going to depend on what? On the height of the tree. So if the tree is not a good tree, the height of the tree is not good, that's why it's going to end up with O of n. Now, if I have a good height, which is in a balanced tree, perfect tree, complete binary tree, that means the height is log of n, and because it depends on the height, that's why it's going to be O of log n. Okay, guys, so the efficiency of a binary search tree will depend on its height. This is just a different wording. So I don't want you in the exam, just because we're changing the wording of something, then you get what? Get confused. Of course, it's going to be what? The efficiency. When we say efficiency, we mean what in this course? Time complexity. We means worst case. Now, we start talking about AVL. An AVL tree is a self-balanced BST. Is this true? Is it? Yes. So let's wait until the voting and then we'll answer this so we don't give them the answer.
I'm not sure exactly what all definition.
Yes, soon we're going to explain it. So what do you guys think? It is true. I think what you mean, James, is that if it's not perfect but almost balanced, if there's only one child different, that's what you mean? Yes. So guys, here the question is, in this case here, this is a perfect tree. It's balanced, but it's perfect, correct? We said if we have 1 or 2 or 3 missing from this, going to be complete binary tree, that's also balanced. Now, with the AVL tree, even if there is a difference of -1 and 1, it's considered balanced. We call it balanced. Even though it's not fully balanced, it's balanced. So when we ask about self-balanced trees, yes, AVL is a self-balancing tree, okay? When I'm dealing with an AVL tree, I will write the height value where? At the bottom of the tree or at the root? So far, with the binary search tree, with everything else, we used to write the height where? The bottom. Up with the BST. So we start from the root with what? 0, 1, 2, 3, and then we end up with the height at the bottom. We said in an AVL tree is the opposite. On the AVL tree, we start from the root. From the root on the AVL tree. Why? If you remember, we said we're going to put the height at the root, and next to each node, it's going to be the height of this node. What would be the 0? The dummy nodes. Okay, the leaves, the dummy nodes are the one that's going to be 0. So here in the 32, it starts with 1 because the dummy nodes are 0, 1, 2. Why 44 is not 3? Because if it's the height of the tree, it needs to go with the longest part. So on the right is longer than on the left, okay? So remember, this is important because when you want to calculate your balancing factor, you're going to depend on this. Okay. Balancing factor is what of a node? We said to calculate it, it's the height of the right subtree minus the height of the left subtree. When is the node considered unbalanced? In which case? When the balancing factor are -1 or 0 or 1, or when they are not -1, 0 or 1, or we should look at the height of the nodes, not on the balancing factor. Which one we explained last time? Exactly. So we look at the balancing factor to figure out if it's balanced or not on the height. But to calculate the balancing factor, we need the height. That's why we're putting the height next to each node. Then we need it to always be -1, 0, or 1. Why? Because that's the only way for us to prove that this is still log of n. If the height only differs with -1. If it differs with more than that, I'm not going to be able to prove that it's log of n, and then it's not going to be balanced. Now, the worst case for search, insert, and remove operations in an AVL tree, not the BST, AVL tree now, what is it?
Just the point of even doing it.
I think we need like a what do you guys think? Log of n or
Elias, this is Elias.
That Jaws.
70% is good enough for me. Why?
Why would it be worse? Why would it be ambiguous? You're resting.
We even explaining AVL. Why did we even arrive at the AVL? Right, guys? Why did we arrive at the AVL? Was the BST? Yes, Riley.
Because we didn't like the BST was ON.
Exactly, because the BST is O of n. So if also the AVL is O of n, I'm wasting my time then here. Correct? The reason we're learning AVL, because it's a bit better, not a bit, a lot better than the BST, because I'm guaranteed to always have O of log n. The problem with the BST that it depends on the height. That means what? If it's a best tree, O of log n, worst tree, O of n. But in the AVL, the tree is self-balancing. Each time the tree is fixing itself to always be log of n. Okay, guys? Now, just the last one before we move. Do you remember when we said the ABC labels? We said when we want to insert or remove something, we want to try to balance the tree. So we start by putting Z, Y, X, but we need to give the Z, Y, X ABC labels to be able to balance them. They are based on what? Ascending order, in order, pre-order, descending order. What do you guys think? Is there something wrong here in the question, in the options? Yes? It doesn't matter, X, Y, Z, Z, Y, X. But with the options, if there's something wrong, do you think? What do you Nothing
Same.
wrong?
Same.
Yes, Anthony.
Option 1 and 2 are the same, aren't they?
Exactly. Ascending order, in order are the same, guys. It's very important for you to know for midterm, final, everything. In order and ascending order, when it comes to BST, not to a normal binary tree, a BST is what is always in the ascending order. AVL is a BST also, so it will apply to it. So the answer is ascending order or in order, not or, both of them, the same thing. Ascending order and order are the same answer. Okay? Very good. So let's go now to continue our lecture.
Score start up. Not real.
So last time we already covered the insert. I'm going to go through it a bit fast with you, and then we go to the removal. Okay, very good. What was the steps that we concluded, guys, is that when I insert something, I find that I insert something here, for example. I check, is this still balanced? Yes, I continue. Is this still balanced? Yes, I continue. Is this still balanced? I figured, oh, no, it's not balanced anymore. So the node that it's not balanced anymore is the one that it's going to be now Z. And then I go down to X. Now, the other way to do it is you do X, Y, Z, Z, Y, X. I find it when you're working, when you're solving it, it's better to do Z, Y, X. It's just easier for you. Then, after that, we do the ABC based on the in order. And then we always have the B in the middle, A left, C left, and then we add the T1, T2, 3T. We're going to see them. And that's how it's going to be balanced. So let's just do this again. What is the height of 54, 62, 48, 50? Who wants to do these? Ida? 54. What is the height of 54? 1. Why it's not 0? Very good. So technically here, that's 0. That's 1. What is the height of 62? 2. Why it's not 1? Because I have 0 here. Why I can't put 1? Always the longest one. So even if I have 0 here, but I'll continue counting from the one which is longer. 1, that means this is 2. Okay. 50 is what, guys? 3. Then here is 4. Okay, very good. Who wants to do now the balancing factors? Riley? So balancing factor of 54 is what?
So the height of the right minus the height of the left.
Exactly. So the height is 0 here. 0 minus 0. 0. Balancing factor need to be what, guys, all the time? -1, 0, or 1. That means this is okay. It's not, it's balanced. I move to 62. What is the balancing factor of 62?
0 minus 1. 1.
0 minus 1. Guys, I don't do the balancing factor equal balancing factor minus balancing factor. The balancing factor is 0. I have nothing to do with it. When I calculate the balancing factor, it's the height minus the height. 0 minus 1, okay? Which is what? -1. Still here, that's still balanced. What is the balancing factor of 50? Who wants to do it? 50. James?
So what we would do is that we'd find, so the left node is 48 and have a height of 1.
Very good.
Because
Very good.
We takes a 62 and it has a height of 2 as we see, so therefore it's not balanced. And
No, so do it step by step. So that's BF. It's the right minus the left. To 2 minus 1, it's still 1. It's still balanced. That's how you're going to think about it. We're not going to look at the height, which is 3, at the balancing factor. So BF, as James said, this is 1, this is 2, 2 minus 1, 1. I'm still good. Very good. Who wants to do the balancing factor for 78? Okay. Which one has a height of 2? 3. Why? Because 0, 1, 2. Always the higher. So 2. That means 1 minus 2. Minus 2. Now minus 2 is not here. That means this is my first unbalanced node. So I'm going to put Z here. What would be Y, X? I'm always going to track to where I inserted. So I inserted here 54. So I'm going to track back where I inserted. Okay? So that's Z, that's Y, that's X. Correct so far? Very good. So now who's going to do the ABC? Let's see new faces. ABC, guys. How are we going to do the ABC? What are the steps to figure out the ABC? Ralph?
We'll do in order.
In order, very good. So in this case here, we know the keys. The in order is ascending order, so it's very easy for me to know what is the in order, right? So let's start. We know that it's what? 17, 32, 44, and what else? So 44, what is the next one for the in order? 48, correct? 50, 54, 62, and then 88, correct? So what is the next step, Rob? So I put the in order. What's the benefit of this in order?
78 and 62, 58, 62.
So just to track things first, so I need to find them. What are the Z, Y, X here? My, the 50 is my what? My Y. X is 62. And then 78 is my Z, correct? Now it's just what? In order. So A, B, C. That means A is Y, that's A. B is X, that's B. And then Z is C. Good, Melanie?
You definitely mentioned it last lecture, but how do we determine which number?
X, Y, Z. Is that's how we did it. So we found the first one, which is unbalanced. This is unbalanced, right? So the first node, which is unbalanced, is Z. Now I track it back to the way that, where did I insert? Did I insert from this side or did I insert from this side? I inserted, that's what I inserted. I inserted 54. So I'm just tracking it back. So usually Z, Y, X, it's always the children. The child of Z is Y, the child of Y is X.
The parent of the node that you just inserted?
Exactly.
And the first unbalanced.
Yes. Yes, definitely. So we check the first I inserted here, and then that's the first one unbalanced. So it has to be between this this root, not another root. When we do the removal, it's going to be a different story. We're going to talk about it. But this one is it clear for everyone, this one? Riley.
Put A and B and C in order when they have their own.
How we're implementing it, or how is the logic? The logic is that we found ABC, correct? The logic is going to be like this. So we're going to always have B, A, C, like this. That's the logic now. Implementation, we're going to talk about it later.
We had 52 as a node on the left, but you put A there and where did we go? Or where did we
Exact. So that's the next step now with the logic. So we said we still have T1, T2, T3, T4 to figure out. These ones are usually, we start from left to right to figure out the T1, T2, T3, T4. From left to right for the ZYX. That means what is the first left node or bunch of nodes connected to the ZYX is here. So that's the first one. What is the next one connected to one of the ZYX? 54. The next one, this one. We're going to treat it as leaf. Now, what is the last one? This one. So it's always going to be T1, T2, T3, T4. And then we're going to put them like this. T1, T2, T3, T4. So that's the logic. That's the rules. Now, in the implementation, coding-wise, we're going to do something called single rotation, double rotation. There is a full code on Java. You can see it, go step by step, try it on the computer. That's a different case. So now let's erase all of this and see what's going to happen. So we found, do you see here, guys, for example, we did X, Y, Z, whatever you're comfortable with. I find it easier to start from Z, Y, X, okay? And these are the in order. So 1, 2, 3, 4. Then we have the ABC. Now the next step is to do the T1, T2, T3, T4. And we're going to do this. So the B, we said B is what? Is 62. A is 50. C is 78, correct? And then we're just taking this whole T1, putting it here, T2, T3, T4. That's what actually happened. Yes, guys. Yes, T1, T2, T3, they go from left to right, okay? But they are the one attached to the ZYX. So which is the first one on the left attached to the ZYX? This one, that's the first one, okay? Then the next one will be this. Third, fourth, that's the process. Now, guys, when I do this thing here in the exam, if you want to check if it worked for you, what are you going to do? Two things. Check, is it still a BST? Is everything here still less? Is everything here still greater? The second thing, recalculate the balancing factor. Okay, so the BF of this one is what? Now, so what is the height here? The height is 0, 1, 2, 0, 1, 2. What is the BF here? 2 minus 2, 0. So it's balanced. That's how we do. Okay, good. I'm going to solve a bigger question for you, but let's go now to the removal and we'll talk more about it. We said we're going to use the in-order traversal. Okay, these are the ones that we're talking about, the T1, T2, yes, sir.
So I just have a question. What if the roots be unbalanced? Going back to that, the one that we just did.
So if the, and this one, this example would be unbalanced. This one here.
The root, the 24.
Yes, very good. So 0, 1, and this one is what? 0, 1, 2, 3, correct? 0, 1, 2, 3, and that's 4. This is 1. That's what? BF equal what, guys? 3 minus 1, that's 2, that's unbalanced, and you do another balance. We're going to see it now in the big exercise that I'm going to do, give you. We're going to do two balancing. So that's normal. You don't stop. But here I'm just explaining the concept so we don't spend too much time on the inserting. We'll move to the removal. We'll do a big one, and we're going to do them both. So again here, guys, you're going to see this. This is another example for the T1, T2, T3. Now the removal. Here it's different, guys. The Z, Y, X, you're going to do the same thing. We're going to start with the first unbalanced node is going to be Z. But you're not going to track it back to the where it was removed. You're going to track it to which side has greater height. Okay, so that's the thing. So let's see one right away for an example. So look, I removed 32. Okay, guys, I removed 32 from here. 0, 1, that's what? 0, 1, 2, 3, that's 4, correct? What is the balancing factor here? 3 minus 1, that's 2. That means this is my first unbalanced, node. So I need to, so this is going to be Z. In the insert, we tracked it back to where we inserted. Here, no. Here we're going to check which one have greater height. This one is 3, this one is 1, so I'm going to go this way. That's my Y. Now the same thing for the Y. To choose X, I need to check which one has a greater height. In this example, both of them are the same. So why did I go to the right? For no reason. I can go also to the left. Okay, so there's two options. Sometimes on the final midterm, we ask you, this is not covered in the midterm, we ask you what are the two trees that can come out from this? You have two options. You can draw them both, for example. Okay, so here, we went here X, and then now we're going to do the same exact thing. What is ABC in this case?
ZYX.
ZYX, 44, 62, 78. It's in order. So this is my A, B, C. I'm going to do the same exact thing. So B is here, A is here, and then C is here. The same thing. What is the first node or bunch of nodes connected to ZYX? This is the first one, this is the second one, third one, and then fourth one. But here we have T0 instead of T1. We started with T0. Good. So if I want to draw this, what's going to happen? So it's going to be like this. Okay. So we had now B, which is 62, 44, 78. Again, as we said, this is not the first. Maybe we went on the left. It's also going to work. It's going to look like this. So do you see these are two different trees? This is the root is 50. Here the root is 62. Both of them are correct. Both of them are fine. Okay. Very good. Any questions about the removal? We're going to have now. Let's talk a bit about the complexity. Who can help me understand why the searching, inserting, removing is O of log n? Other than that, we saw them in the WOOC lab earlier. Like, who wants to explain the logic behind it? Let's see. What's your name again? Not Munir, what's your name?
Nabil.
Nabil.
So, well, for searching, the reason why it's O of log n is just simply because in an AVL tree, it's already balanced. So we already know that like your height is going to be log of n. So for the first one, that's
Very good. So again, guys, the whole idea is everything is based on this. That's why I focused a lot on the O of h. Everything that we're going to do is based on the height. Now, how did we prove that the height is? So if I do this and I go back here, because you're not going to trust me, I'm sure. So we go here. We had all of this mathematical stuff. We started by this, if you remember, and we end up with O of log n. So we actually proved it mathematically that it's going to be O of log n. Sorry, the height is going to be log n. Actually, the height is going to be 2 log n. But we said that means O of log n, okay? This reminds us with, if you remember, with the complete binary tree, we were able to prove it as log of n, but in the perfect binary tree, it was, if you remember, something log of n plus something, but this is 2 log n. So all of them will go back to O of log n. Very good. So we already proved this. We don't have to prove it each time. So when we go here, we can actually say the height is log of n, because we proved it. Everything depends on log of n. Now, if I want to find something, my worst case, if my height is like this, for example, let's say you have something like this, for example. Now, if I want to find something, this is my height. The worst case will be I'm trying to find this one here, right? So I'm going to go to log of n. Now, but why is inserting also log of n? Because if I'm inserting, I need to first maybe find it. I need to replace it, rebalance, all of these things. So there's multiple steps for this. The first thing is I want to insert something. So if this is 50, I want to insert 62. I actually have to go through this because it's a BST, so then I will go here. So I'm searching where can I insert, right? Because I need to keep it BST. So the first step, step 1, is costing me log of n, because I'm searching where should I insert my node, correct? We all understand this part. Now my step 2 is what? After I insert something, what do I need to do? Before balancing, well, what if it's balanced? What if it doesn't need rebalancing? So the second step is to find Z, right? If it needs to balance. If I want to find Z, let's say I insert something here. That's my new one. I need to keep going up till I find the unbalanced one. What if I kept going, and this is the one unbalanced on the root? That means what is my worst case to find Z? Also log of n. So this is going to cost me log of n. Now the rebalancing. The rebalancing is what? Code-wise is constant, because we're going to use this with a linked structure. So we're just going to change the pointers. If you have a linked structure, if you just want to switch something, is you're going to say, okay, instead of this pointing to a parent, okay, now I'll point to something else. So this is what O of constant. That means log of n plus log of n to log of n, it's still O of log of n. That's why even the insert is this. Now remove element, the same exact thing. I need to find Z first. I need to do rebalancing, all of these things. So it's going to end up with also log of n. Okay? So you don't doubt me when you go home and reflect on this. Now, this is a summary of what we talked about from the book. And then here, you may find, yes. And
Can you go back to the previous slide?
Yeah.
Yeah, for the insert item, I just have a little question about step 2, where we
Yeah.
have to find Z. So in finding Z, the operation that we need to do is finding the height, like imagine we have a node, we have to find the height at the leftmost, at the.
no, this is insert, not removal. Insert, you're just going upwards from the insert.
On the balancing factor, don't we know don't we need to know the height of the left subtree and the right subtree?
Yes.
Finding the height of the left subtree would mean finding the height of like every single node.
That's the thing. If you look at the code, I usually have, by the way, the codes for everything. I'm not sure if you noticed it. I took them from the slides and I put them in something called Java implementation. If you look at the Java implementation, you will know that, for example, call for the height and stuff, these are all constant, all of them. There is a way that everything is all constant. Yeah. So now, guys, in the book, if you look at the book, you're going to see that they talk about single rotation, double rotation, all of these things. So these are stuff that the concept of when you're implementing them in Java, use the idea of single rotation and double rotation, which is just changing the pointers. Why? Because we want to keep steps constant. We don't want to say, okay, I'm going to have a loop until I make it good. I want to actually know. There is a way that, for example, let's go right away to this. Let's see, can I, yes. So if you look at this, when I have the ABC, why is this a single rotation? Because I can just change the pointers somehow. So I'll point this to the parent, and this one will point it, I'll change the pointers. It will take me only a single rotation to be like this. So I'm just bringing this down, okay? Now, the same thing here. But here, in this case, I cannot do it from a single rotation. Let's say I want to rotate X to the right. What's going to happen? I'll have X here. Doesn't solve anything. If I want to, I cannot even do it on the left, right? So that's why I need double rotation here. What does it mean? It means the first rotation that you're going to move this to the right, it's going to now look like this again. And then you do another rotation to move like this. So that's just the idea of single rotation, double rotation. There is lots of more information in the book about this. You can check it, but you're going to find some of the YouTube videos online if you're searching how to solve the AVL trees and do the rebalancing. They base the rebalancing itself on single and double rotation. My opinion that no, follow this if you want to solve it, I mean on paper. This one is actually, it's implemented with code-wise, but I mean like you'll find people helping you to solve things on paper. Always follow the BAC in the exam and the midterm. That's much, much simpler. Do the in order, A, B, C, and that's it. You don't have to learn the single and double rotation. Now, these are some notes. So let's go now to the solving the exercise, then you'll be able to understand it better. Again, guys, if you go here, Java implementation, and you go to the Java implementation of the AVL, you're going to find all of the everything here. Shows you that we're actually using a linked list to be able to do this because we're going to change the pointer. It tells you how you're going to, which is based on the relink. You're relinking the pointers and all of these things. So you can take a look at it. And also, of course, in the labs, you use these things. So if I want to go to this one, now let's do this together. In the exam, this is one of the quizzes that we gave last year. We had this huge tree. Now I made it easy on you guys, and I did all the height and the balancing factor for you. So it's easy. We want to remove 4. What's going to happen? Who wants to help me now? I removed 4. We're going to solve it together, right? Yes.
Check the balancing factor.
Yes. So what is the balancing factor for 7? Sorry? Yes, so the height here is 3, the height here is 1. So balancing factor here is going to be what? 3 minus 1, that's 2. I already found my first unbalanced right away. So what's going to happen in this case, guys? Someone else. So I found the balancing factor, Melanie. Z is what? 7, that's my first one. Now y, not why you found Z, y. So why does it, do I go to 3 or to 23 and y?
Those couple ones.
23, why? Very good. So that's what I want you to always understand. Even though I removed from this side, I don't follow the side that I removed from like I do with the insertion. This has height 3, this has height 1. I'm going to always go here. Very good. Who wants to do the x? Thank you, man. X. Riley.
13, the same reason.
The same reason. Height is 2, height is 1. I'm going to go here. X. Very good. What is my next step, guys? ABC. How can I find my ABC? Who wants to do it? Want someone new? Who wants to introduce himself or herself to me for the first time? Bas.
You have to do.
Sorry, so you had your hand raised? You had your hand raised or no? I thought you had your hand. Bas.
You have to do in order.
In order. What is the in order here?
Ascending.
Ascending. So it's easy for us. 3, 7, then what? 11, 13, 17, 23, 24, and then what? 30. Okay. So what are you going to do?
Oh, you need to label what's your Z, Y, and X.
Z, Y is 23, X is what? 13, X. See, now we're doing it them slowly, step by step, very boring thing. At the exam, hopefully this should be like this for you guys. Like this, it's not going to take time from you. Yes. Yes, you can do that. The reason I'm teaching you this step by step, baby steps, boring thing is that what if in the exam I don't give you the keys, I give you something else. I want you to know the actual general way to do it, and then you can find, like maybe you're going to find something even easier than what I'm teaching you. That's fine. So that means we have what here? The A is Z, correct? The B is what? X. The C is Y. So what are we going to do here? B, A, C. Now, before we do that, what are the T1, T2, T3, T4? Who wants to give me this very quickly? Ahmed.
T1 is 3.
That's T1.
13, 17.
Okay, very good, guys. I don't want anyone to do that T2 is only 13. It's the whole thing connected. And then T3, that's 23. Sorry, that's T3. T4 is what?
Feel like 30.
Everything here. So let's see how this is going to look like. You see, I have all these step by step for you guys if you want to review them. And then, no, I think we made a mistake. We made it, it's not 13. Because X, so 13 is not included, sorry. Right? 13 is X. So what's connected? So connected, this is connected to Z. T2 is connected to X, T3, T4. Okay? Now it's clear, guys. So that's why it's not the whole thing. Okay, so that's my first one. Now, I don't stop here. I need to continue searching for, maybe there is another unbalanced nodes. So in this case, I do this. I need to continue. What is 30? What is the balancing factor for 30? I have H equal 5, I have H equal 3. Balancing factor here is 5 minus 3, 2. That means that's my other Z. Okay, guys? Where I'm going to go with the Y, that's H5, so that's my Y. Where am I going to go with the X? Who wants to try? Yes? 51, exactly, because here is H equal 4, H equal 3. So that's my Z, Y, X. Now the in order is very obvious, correct? Yes, Bas.
So to choose your Z, Y, X, it depends on whichever one has a bigger height.
Yes. Z is your first unbalanced one.
Yeah.
After that, it depends on which one has a bigger height.
What if they both have the same height?
It's up to you, yes. Both answer will be right. So now here, guys, the ABC is very obvious, 30, 51, 72, correct? So if you see it here, we have the 30, 51, 72, that's obvious. Then what are our A, B, C? In this case, that's A, B, C. What is connected? Then you're going to do the T1, and then T2, T3, T4. Now, why I'm saying this? Because in the quiz, the question was, what would be the root at the end of the rebalancing? The problem that was made by student that after they finished this, so they did the rebalance here, they said the root is 30. But this is not an AVL tree anymore. So it's a mistake. You need to continue searching, and then now, after you finish everything, the root will be 51 in this case, because this is B. Is it clear? Okay, now there is another, in the tutorial, there is one about insertion and removal. There is a video about it. You can watch it. And you can go to the Monday tutorial. I would recommend that you watch it and you go to the Monday tutorial if you have questions. If it's easy for you, you don't have to go to the tutorial. Now I'm going to leave it like this. We're not going to do a new chapter or new topic or anything for you guys. If you want to leave, you can leave. If you want to stay to ask me questions about anything not related even to the AVL, general, let's say you're studying for the midterm, you can ask.